Street Physics.
All right, let me pose a question to you. If I had a real simple circuit, I got a battery, and I got some sort of load. In this case, I draw it as a resistor, and so this has a voltage V, potential difference from here to here. That causes current to flow like this around the circuit, and we have a resistance here. I have a question for you. There is a current flowing through here, right? This I, and there's a potential difference like that. Could you figure out what you get if you multiply voltage times current? Could you figure that out? What is this? Voltage times current. You can figure that out. If you know what voltage is, look up what's voltage. What's voltage, right? And what's current. And you can figure that out. It's a very valuable thing, this product of voltage times current. I'll give you a moment.
Pause the video now.
All right. Well, hopefully you were able to figure it out. These things aren't that difficult. Some of them aren't that difficult. What's voltage? It's energy per unit charge. Just look that up in your Regents reference table. What's current? It's the amount of charge that passes divided by time. All right. So if I multiply these two together, what do I get? What is that? What is that? Energy per unit time. That's power. That's power. So voltage times current tells you, if you multiply the voltage times the current across an object, that is the amount of power being either delivered to the object or being supplied. If it's a source of a potential difference, it's the power supplied. If it is a load, some sort of load with a voltage drop, that is something that it uses power. And power is voltage times current, right? And that's a real important relationship. Real simple. It's in your reference table. And then if we can use it, we can find these other relationships too. Well, we know that V equals IR, right? Because we have this relationship. So therefore, V, which is IR, is I times R times I, which of course is I squared R, right? So power is I squared R, or I know that I equals V over R, so therefore substituting there then for there, I got V times V over R, which is V squared over R. So power is voltage times current, or I squared R, that one, or that one. Those are really convenient relationships. And let's try a problem in your notes after the power slide. It says a light bulb operating at 120 volts draws a current of half an amp for 240 seconds. What is the power rating of the lamp? And if you take a look at especially the old incandescent lamps, they would say 120 volts, and then they would have some sort of power rating. And the power rating was always rated at it would say at 120 volts because it's only going to use up that much power if you put it across 120 volts, which conveniently is what the wall is, right? So when you plug it into a standard outlet, it is that. So we got a light bulb. Let's say that's our light bulb, and the voltage across it is 120 volts, and has a current of 0.5 amps going through it due to that. What is the power rating of how much power is this thing using? All right, that's kind of straightforward. Power equals VI. Now, it doesn't matter how long it's on. How long it's on does determine how much energy it uses, but not the rate at which the energy is used. The rate is power Voltage is 120 volts. Current is half an amp. All right, so I guess that's 60 watts. It's a 60 watt light bulb. All right. Could you calculate the resistance of that? Sure you can. Why don't you do that right now?
Pause the video now.
I'll do it too. All right. All right. R equals V over I. So it's 120 volts divided by half an amp, right? Which is, I guess, 240 ohms. That's the resistance of that thing. Well, I wonder if I could put it in my other. I wonder if I could calculate it like this. I wonder if I could say power equals I squared R. Why don't we try that? Power equals half an amp times R, 240 ohms. Oh, we still get 60 watts. All right, so that was power.
Extreme physics.